So this is your camber. This is C. So at this x, here is the tangent to the camber. So in particular, this angle is theta camber, okay? The tangent of the camber curve. And we have u infinity right here. This is u infinity. This angle with the horizontal is alpha, okay? So this small angle is alpha minus theta camber. I need the normal component. I need the normal component, this normal component. So V normal, I'm sorry, due to gamma, plus V normal due to u infinity, this is V normal total. This should equal how much? Should be what?
0.
0, very good. This blue guy is downward. Probably I need to multiply by cosine angle, but we're assuming small angles. So cosine small angle is almost unity. So I have this guy. So the blue component due to gamma is negative because it's downward. Gamma dx over 2 pi x minus x dash. But this is not the total V due to all the gammas. This is due to only one of them. And I need to sum all of them because it's continuous. The summation becomes an integral, okay? This guy plus the other one. Can you tell me what's the other one, the green one? So this angle is alpha minus theta. Is it cosine or sine? Cosine or sine? Alpha minus theta camber. Okay, just rearranging terms. So you have 1 over 2 pi integral from 0 to c gamma of x dash dx dash over x minus x dash equal to u infinity. And again, sine small angle is the same as the angle in radians because we're linearized theory, small disturbance. Alpha minus theta camber, this is the tangent to the camber curve. So it's simply dy camber by dx, right? And this is your governing equation. This is what? As you expected, Leo, this is an integral equation for circulation. It will be always like this. Even in unsteady flow, even in three-dimensional flow, it will be always similar to this picture. An integral equation for circulation. As long as you're using the method of singularities, you're throwing a bunch of continuous singularities in your domain, you'll always get an integral equation for circulation. Okay? Circulation distribution. This is the unknown. Any question about that? Please, if you have any question, I mean, it's not very different from unsteady flow. We will have a very similar picture. So this is why we're doing review. Any question, please? If you have a question, stop me. Don't feel shy. So this lecture is almost, yes, we're relying on concepts from before, but for the derivation of this equation, we almost rely on nothing. This is almost a new thing. So if you didn't study, if you didn't do homework 1, that's fine. Just come up with your question. Okay? So if you're clever enough and you solve this equation, and I'll tell you how in a minute, you will get the circulation distribution, a function of x, maybe x squared, 1 over square root x, whatever. It's a function of x. Okay? If you have this guy, let's see what do we have. If you got the gamma of x. So remember we derived this before. So if you have a distribution of circulation here, for testing distribution, so you have delta u and delta u the other way around. If you remember this, We already derived this relation before. We derived the relation between gamma and delta u. Simply delta u at any x is 1/2 gamma at that x. So you have the velocity distribution over the airfoil. Okay? We derived this already before. So if you got the gammas, here is your velocity distribution, and we know that the Cp distribution is already 1 minus u squared over u infinity squared. So the delta Cp, which is Cp lower minus Cp upper, is u upper squared minus u lower squared divided by u infinity squared, which is u upper is u plus delta u, and u lower is u minus delta u. Of course, this is an assumption that the change in velocity is symmetric up and down. It's not, or asymmetric up and down. So if you neglect the higher order terms in delta u, meaning delta u squared, so this guy goes away, and these guys are small, the square term of it. So we'll get what? We'll get 4u infinity delta u divided by u infinity squared, which is 4 so it's 2 gamma over u infinity. Okay? So if you got your gamma, someone helped you to solve this equation, complicated equation. Here is the velocity distribution, here is the pressure distribution, and if you integrate the pressure distribution, you get the lift. And we can get the lift from another way. We already know that. We already know that the lift is rho u total gamma, and the total gamma is simply the integral of all the circulation, right? So if you divide everything here by 1/2 rho u infinity squared c to get the lift coefficient, this will be 2 this integral over u infinity c. So here is your lift coefficient. Okay? So in other words, in conclusion, if you solve this integral equation, you have anything at your disposal. In particular, I just here summarize the interesting ones: velocity, pressure, and lift. But you can get whatever you like. You can get the velocity field at any point, pressure at any point, and so on and so on. Any question, please? Any question? Any question? And like I said, I mean, you don't need to waste all your time writing after me. This is already posted. You can just watch. You know, it's not that interesting to watch, but you know, just save you some time. So what we're going to do with this integral equation for circulation, I'll write it here again because it's very important. 1 over 2 pi from 0 to c gamma of x dash dx dash over x minus x dash equal u infinity times alpha minus dy Kimber by dx. Okay? This is your integral equation. What we're going to do, yes, Amir?
So can we, if we put other singularities, like a combination of singularities, doublet, source, sink, vortex. So the left-hand side of your velocity will change, right? So you need more integrals for...
That's right.
Right. So for addition of each new element, you need new boundary conditions to satisfy it. Is that correct?
Yeah. So, so if you add sources, if you add sources, that's fine, but the condition will be because a closed body dictates that the total sources sink equal to 0, so this is an equation. You're going to keep adding equations. But of course, if you make it too complicated, you might not have sufficient, you know,
conditions.
yeah. But yes, you're right. So one of the ways to do it, if you change your singularities to allow for viscosity, okay? So I can replace these gamma. So this is one of the actually the things that I will propose as a project, okay? Is to change these gammas instead of gamma over 2 pi r. This is very simple, right? If you look at the derivation is indeed very simple. It's just one line, right? It's v gamma plus v due to u infinity is equal to 0. And V2 to gamma, we know this relation gamma over 2 pi r because of the velocity due to a vortex. It's gamma over 2 pi r. This is already known. This is valid for potential flow. So it already satisfies Laplace squared phi equals 0. But I can opt out of potential flow and look at viscous flow, for example. Then you will get a different relation. It's not gamma over 2 pi r, it may be one of the ones that you have seen in the homework. Okay? We have already viscous models for vortices. So you can put this guy, okay? And then you can also put not only vortices, you can also put sources, viscous sources. And you have two unknowns, and you need two boundary conditions. Of course, you have the no penetration boundary condition. This gives you an equation. What is the other equation? Can you suggest another equation in a viscous formulation? What will be a good boundary condition in a viscous formulation? If you account for viscosity, what other condition? So we already said the flow normal to the surface to be 0. Okay? This has to be satisfied in any flow. But what else has to be satisfied in a viscous flow? The tangential component, right? So the tangential to the surface now we have to dictate that it's equal to the speed of the surface. So if it's stagnant, it will be 0. Two equations and two unknowns. So this is the viscous extension of this work. It's not very well known, and like I said, I'll propose it as one of the projects. You can